Hello guys, today we are going to derive pi formulas through the inverse tangent function, and we will do it through the integral representation of the inverse tangent function. So this is the integral representation of the inverse tangent function. So we would now kind of transform this integral into an infinite series. And how could we do it? Basically, we would derive an infinite series expression for this rational function, and we could do it by the geometric series formula. As we all know that the sum n goes from 0 to infinity of x to the n converges to 1 divided by 1 minus x, and there is a condition that the absolute value of x needs to be less than 1. Now we would do what? That we will plug in x is equal to negative t square, and if we plug in that, we would exactly have this rational function in the form of an infinite series. So we would get here the infinite series of n goes from 0 to infinity. So the negative sign with the n will become a negative 1 to the n, and this t square will become t to the 2n with the property of exponents, and here we will be left with 1 divided by 1 plus t square, and the same condition will apply here. The absolute value of t also needs to be less than 1. And now we have an infinite series representation of this rational function, and now we could plug in this infinite series into our integral. So we would be left with the integral from 0 to x of the sum n going from 0 to infinity of negative 1 to the n t to the 2n, and this will equal to inverse tangent of x. The equality will obviously stay the same, and now I will rub the board and we will continue it again. So far we have reached this point, and now we are going to interchange the sum and the integral. And with respect to the variable t, this negative 1 to the n is a constant term, so we could bring that outside. So far we have reached this point. Now we have to evaluate this integral. This integral is very simple integral. You evaluate it and you would get x to the 2n plus 1, and this would equal to the inverse tangent function. Now we are going to do some substitutions. So we multiply both sides by 1 over x, and we would be left with this sum. So far so good. So far we have reached this identity, Now we will substitute x is equal to square root of k, and we were left with the infinite sum n going from 0 to infinite of -1 to the n, and the square root sign and the 2 in the exponent will cancel each other, and we were left with just k to the n. As we have substituted, this will become square root of k over square root of k. So, and there is obviously a condition that we are not mentioning. We have mentioned it earlier, but we will mention it again, that the absolute value of k needs to be less than 1. So this is our formula, and we will just plug in values into it. So now I am going to take a special move. I will take a limit of this expression as k approaches 1, and so we will be left with if so. I will rub the board and we will get to it. So far we have reached this point. Now we will discuss this side. So if you put k equal to 1 here, you would see that this series converges uniformly, and the right hand side, as we put k is equal to 1, also is not a problem at all. So we could safely put the value k equal to 1 here, and we would get this. And we put k equal to 1 here, we would be left with inverse tangent of 1, and that equals pi by 4. And this is our first formula, and you would know this formula as the Madhava-Leibniz series, and this is a very famous one. But we are going to derive a second series which is a quite not famous. So we are now going to put k equal to 1/3. And this would equal to the inverse tangent of 1 divided by square root of 2, 1 divided square root of 3, sorry, and the 1 divided by square root of 3 in the denominator will come into the numerator and become square root of 3. And as we all know, the inverse tangent of 1 divided by square root of 3 is just pi by 6, and we will multiply it by root 3. Stays the same. Now we will clean the board and we will get to it again. So far we have reached this point, and now we could simplify this thing as the following. 6 can be factored as 3 times 2. Okay, and we could now bring a rational denominator through dividing the numerator and denominator by 1 divided by square root of 3, and we would be left with pi divided by 2 times 1 divided by square root of 3. And now what we will do is we will multiply both sides by 2 root 3, and we were left with 2 times root 3 times this infinite sum going from 0 to infinity of -1 to the n divided by 3 to the n times 2n plus 1 equal to just pi. And now there is a bit simplification you could do here. You could take this 2 inside the square root and make this a 4, and then 4 times 3 will become square root of 12, and this will become our final second formula. So guys, this is our second important formula, and we will clean up the board and we will kind of compare the both series. So these are the two formulas we have derived today. So which formula is better, do you think? My opinion is the first formula. You would say why? That is because this formula has smaller terms compared to this formula, and so this formula converges quite faster than this formula. So this is a plus point, that this converges faster, and this has a minus point, that this converges slow. But there is also a problem in the first formula, I think, that is the square root of 12. This irrational needs a lot of digits through which we could evaluate this whole sum, and so that is a minus point of that, and the calculation of this series is quite easy, I could say. But my opinion will stay the same, this series. Share in the comments which series do you like. Thanks for watching.